Welcome! In this session, we'll be tackling problem number 1951, all the pairs with a given sum. This is an interesting problem that explores fundamental concepts in array manipulation and algorithm design. Let's dive in and explore how to approach solving it. In this problem, you are given an integer array called nums and a specific integer value called target. The goal is to find all unique pairs of integers from the array that add up to this target value. A pair, represented as a, b, is considered unique if no other pair contains the same two integers, regardless of their order. For example, the pair 1, 5 is treated the same as 5, 1. The result should be returned as a list of lists, where each sublist represents one of these unique pairs. Furthermore, each pair must satisfy the condition that a plus b equals the target, and the pairs can be listed in any order in the output. The nums array can contain up to 10,000 elements, and both the integers in the array and the target value can range from -1 billion to +1 billion. This means the solution must handle potentially large inputs efficiently. To clarify with an example, if the input array nums is 1, 2, 3, 4, 5, and the target value is 6, the output would be 1, 5, 2, 4. Here, the pairs 1, 5, and 2, 4 both add up to 6, and no other unique pairs can be formed that satisfy this condition. In another example, if the input array is 3, 3, 4, 4, 5, 6, with a target of 8, the output would be 3, 5, 4, 4. This is because the pairs 3, 5, and 4, 4 are the only ones that add up to 8. Notice that even though there are duplicate values in the array, we focus only on forming unique pairs. Now, consider a case where the input array is 1, 1, 1, 1, 1, and the target is 2. The output in this case would be 1, 1. Here, the pair 1, 1 satisfies the condition, and even though there are multiple 1s in the array, only one unique instance of the pair is returned. This ensures that duplicates are avoided in the result. The problem also comes with constraints to guide the solution. The array nums can have a length of up to 10,000, and the range for each element as well as the target is extremely large, going from -1 billion to +1 billion. Therefore, the solution must be designed to handle these constraints efficiently. Additionally, it's important to note that the order of the integers in a pair does not matter. A pair like a, b is considered the same as b, a, so duplicate pairs must be excluded from the result. When thinking about edge cases, if the nums array has fewer than 2 elements, it's impossible to form any pairs, so the output should be an empty list. Similarly, if no 2 numbers in the array add up to the target, the output should also be an empty list. If all elements in the array are the same and their sum equals the target, the result should still include only one unique pair. Lastly, because the array can be large, the solution must be implemented efficiently to avoid exceeding time limits, especially when processing edge cases or large inputs. To tackle this problem, one of the first approaches we can consider is the brute force method. The intuition here is simple: we systematically check every possible pair of numbers in the array to see if their sum matches the target. This involves using 2 nested loops, one to pick the first number and another to pick the second number. If we find a pair that meets the condition, we store it in a set, ensuring that only unique pairs are collected. While this approach is easy to implement, its major drawback lies in its inefficiency for larger arrays. The time complexity is n squared due to the nested loops, and while the space complexity is relatively low, only requiring storage for the unique pairs, the trade-off in performance makes it impractical for larger inputs. This simplicity can be helpful for small datasets, but we need to explore more efficient methods for scalability. A more efficient method we can use is the two-pointer approach, which leverages the power of sorting to reduce the number of pairs we need to examine. The idea is that by sorting the array, we can strategically use 2 pointers, one starting at the beginning of the array and the other at the end. By calculating the sum of the numbers these pointers reference, we can determine the next steps. If the sum matches the target, we record the pair and move both pointers inward. If the sum is less than the target, we move the left pointer to the right to increase the sum. Conversely, if the sum is greater, we move the right pointer to the left to decrease it. This method also includes a mechanism to skip over duplicate numbers, ensuring that only unique pairs are added to the result. While this approach is much faster than brute force, with a time complexity of O(n) log n. Due to sorting, it does require the input to be reordered, which may not always be desirable depending on the problem constraints. Another optimized approach involves using a hash map to achieve even better efficiency. Here, the intuition is to use a hash set to keep track of the numbers we've already seen as we iterate through the array. For each number, we calculate its complement, what we would need to add to it to reach the target sum. If the complement is already in the hash set, we know we've found a valid pair and can add it to the result set. If the complement isn't present, we simply add the current number to the set and move to the next. This method avoids the need for sorting altogether, preserving the original order of the input. Importantly, it achieves a linear time complexity of O(n), as it processes each number only once, and the space complexity is O(n), due to the storage required for the hash set. This approach is particularly efficient for larger datasets, offering a significant improvement over both brute force and the two-pointer technique. Among the approaches discussed, the hash map strategy stands out as the optimal solution for this problem. Its ability to find pairs in a single traversal makes it well-suited for handling larger inputs efficiently. Unlike the two-pointer method, it avoids the overhead of sorting, which can be a significant advantage when the order of the input array needs to be preserved. Additionally, ensuring the uniqueness of pairs is straightforward with the use of a result set. By leveraging the hash map to check for complements in constant time, we achieve a much faster solution compared to the brute force method. These factors make it the clear choice when prioritizing both time efficiency and simplicity. The hash map approach is chosen because it strikes the best balance between efficiency and practicality. Compared to brute force, it drastically reduces the time complexity from O(n)² to O(n). Compared to the two-pointer method, it avoids the need for sorting, maintaining O(n) efficiency while preserving the original order of elements. The trade-off for this speed is the additional memory required for the hash set, but this is a reasonable compromise given the performance gains. While the brute force or two-pointer methods may suffice for smaller inputs, the hash map approach scales better and remains the most robust solution for larger datasets. Overall, this strategy provides an elegant and efficient solution to the problem, ensuring both accuracy and speed. To begin, the problem is to find all unique pairs of integers in an array that sum up to a given target value. For example, if the array contains numbers like 2 and 3, both adding up to the target, we only want to count that pair once, regardless of their order. Now, the brute force approach involves iterating through all possible pairs in the array. This means using two nested loops to check whether the sum of any two numbers equals the target. To ensure that we don't count the same pair multiple times, we can store the pairs in a set, because sets inherently prevent duplicates. While this approach is straightforward, it's not the most efficient, as we'll see in the next steps. Here's how the brute force approach works step by step. First, we initialize an empty set to store the unique pairs we find. Then, we loop through the array using two nested loops. The outer loop picks one number, and the inner loop checks all subsequent numbers to form pairs. For each pair, we calculate their sum. If the sum matches the target, we add the pair to our set. To ensure uniqueness, we store the pair in a consistent order, such as always putting the smaller number first. Finally, we return the set of unique pairs as our result. However, this approach has a time complexity of O(n)², due to the nested loops and a space complexity proportional to the number of unique pairs we store. Now, to optimize the solution, we can use hashing to reduce the time complexity to O(n). The idea is to use a hash set to keep track of the numbers we've seen so far. Instead of iterating through the array multiple times, we can check in constant time whether the complement of the current number exists in the set. The steps are as follows. First, initialize two empty sets, one for storing numbers we've seen and another for storing unique pairs. As we loop through the array, we calculate the complement of the current number with respect to the target. If the complement is already in the scene set, that means we've found a valid pair. We then add this pair to the pairs set, ensuring it's stored in a consistent order. Finally, we add the current number to the scene set. This approach significantly improves efficiency while maintaining correctness. There are a few key insights that make this approach effective. First, using a set for unique pairs is crucial because it automatically prevents duplicates. This is important since the problem requires us to count each pair only once, regardless of order. Second, hashing dramatically improves efficiency by allowing us to check for the complement of a number in constant time, instead of iterating through the array for each number. Lastly, we need to handle several edge cases to make the algorithm robust. For instance, if the array is empty or there are no valid pairs, we simply return an empty set. Additionally, when the same number appears multiple times in the array, we ensure that we only include valid, unique pairs by storing them in a canonical order, such as always sorting the pair as min, max. Let's go through an example to see the optimized approach in action. Suppose the input array is 1, 2, 3, 4, 5, and the target is 6. We start with two empty sets, one for seen numbers and the other for unique pairs. As we iterate through the array, the first number is 1, and its complement with respect to the target is 5. Since 5 isn't in the seen set, we add 1 to the seen set. Next, the number 2 has a complement of 4, which also isn't in the seen set, so we add 2. The same happens for 3, whose complement is also not found. Now, when we reach 4, its complement, 2, is already in the seen set. So, we add the pair, 2, 4, to the pairs set. Finally, the number 5 has a complement of 1, which is also in the seen set, so we add the pair, 1, 5. At the end, the unique pairs are 2, 4, and 1, 5. This process is efficient with a time complexity of O(n), as we only traverse the array once, and the space complexity is proportional to the size of the sets. This solution efficiently finds all unique pairs in an array that sum up to a given target. The method uses a dictionary to store the frequency of numbers encountered while iterating through the array and a set to store unique pairs. Here's a breakdown of the code. 1. Initialization. A dictionary scene is created using defaultdict to store the count of each number encountered in the array. A set unique underscore pairs is initialized to track unique pairs. 2. Iteration. We iterate through each number in the array ARR. 3. Complement check. For each number, its complement is calculated as target number. If this complement exists in the dictionary scene, it means we have encountered a number that pairs with number to form the target sum. For storing pairs, pairs are added to the unique underscore pairs set in sorted order using tuple, sorted, number, complement. This ensures that pairs like 2, 3, and 3, 2 are treated as the same pair. 5. Updating dictionary. After checking the complement, the count of the current number is increment in the dictionary. 6. Returning results. Once the loop is complete, the set of unique pairs is converted to a list and returned. This approach ensures that duplicate pairs are avoided due to the use of a set, and the algorithm operates in O(n) time complexity for most cases, where n is the length of the array. This is the Java implementation for LeetCode problem number 1951, all the pairs with a given sum. The logic mirrors the Python implementation, using a hash map to track numbers and a hash set to store the unique pairs. Key differences include Java-specific collections like hashmap and hashset, explicit type declarations, and converting the pairs to sorted lists for uniqueness. The method efficiently finds all unique pairs that sum to the target. Let's start by looking at our first example where the input array is 1, 2, 3, 4, and the target sum is 5. The goal is to find all unique pairs of numbers that add up to this target. We begin by initializing two data structures, a dictionary called scene to track numbers we've encountered, and a set called unique underscore pairs to store the valid pairs without duplicates. Now, as we iterate through the array, the first number we encounter is 1. To find its complement, we subtract it from the target, resulting in 4. Since 4 isn't in the scene dictionary yet, we add 1 to scene and move on. Next, we process the number 2. Its complement is 3, which, again, hasn't been seen yet, so we add 2 to scene. When we reach the number 3, we calculate its complement as 2, and this time, 2 is already in scene. This means we've found a valid pair, 2, 3, which we add to unique underscore pairs in sorted order. Finally, when we reach 4, we calculate its complement as 1, which is also in scene. This gives us another valid pair, 1, 4. After processing the entire array, we update the scene dictionary to include 4, and our final states are scene containing all the numbers from the array and unique underscore pairs holding the pairs 1, 4, and 2, 3. To generate the output, we convert unique underscore pairs to a list and return it. This gives us the result 1, 4, 2, 3, which matches our expected output. Now, in the second example, we introduce duplicates in the input array. The array is 1, 1, 2, 3, 4, with the same target of 5. As before, we initialize scene and unique underscore pairs. The first number is 1, and its complement is 4. Since 4 isn't in scene, we add 1 to scene. When we encounter the duplicate 1, we calculate the same complement, 4, and again it's not in scene. We increment the count of 1 in scene but don't add any pairs yet. Moving on to 2, its complement is 3. Since 3 isn't in scene, we add 2 to scene. Next, we process the number 3. Its complement is 2, which is already in scene. This allows us to form the pair 2, 3, which we add to unique underscore pairs. Finally, we encounter 4. Its complement is 1, and since 1 is in scene, we add the pair 1, 4 to unique underscore pairs. At this point, scene contains all the numbers from the array, and unique underscore pairs includes the pairs 1, 4, and 2, 3. Converting unique underscore pairs to a list gives us the final output 1, 4, 2, 3. Notice that the duplicates in the array didn't affect the result because we used a set to track unique pairs. This ensures that even if the same pair can be formed multiple times, it only appears once in the output. Now let's examine an edge case where no pairs can be formed. In this third example, the input array is 1, 2, 3, and the target sum is 10. As before, we initialize scene and unique underscore pairs. Starting with the first number, 1, we calculate its complement as 9. Since 9 isn't in scene, we add 1 to scene and continue. The next number is 2, and its complement is 8, which also isn't in scene, so we add 2 to scene. Finally, we process 3, whose complement is 7. Since 7 isn't in scene, we add 3 to scene. After iterating through the entire array, no valid pairs were found, so unique underscore pairs remains empty. Converting it to a list gives us an empty result, which is the expected output for this case. This example demonstrates that the solution correctly handles scenarios where no pairs meet the target sum condition. In this solution, the time complexity is O(n), where n represents the number of elements in the input array. Let's break it down step by step. First, we iterate over the array using a for loop. This loop processes each element exactly once, which contributes O(n) to the time complexity. Next, for each element, we check if the complement, which is target number, exists in the dictionary called scene. Dictionary lookups are O(1) on average, so this operation only adds a constant time per iteration. Additionally, when a complement is found, we add the pair as a tuple to the unique underscore pairs set. Adding to a set and sorting a tuple, which involves only 2 elements, are both constant time operations, or O(1). When we combine these steps, the overall time complexity becomes O(n) multiplied by O(1), which simplifies to O(n). Finally, it's important to note that this complexity remains O(n) across all scenarios, whether best, average, or worst case, because each element is processed once, and the dictionary and set operations consistently take O(1) time on average. Now, let's analyze the space complexity of the solution, which is O(n). Here's the breakdown. The dictionary named scene is used to store the elements we've encountered so far. In the worst case, if all elements in the array are unique, the dictionary will store all n elements, requiring O(n) space. Then, we have the unique underscore pairs set, which stores distinct pairs of elements that sum to the target. In the worst case, if every pair of elements contributes a valid sum, the set can grow to O(n)/2 pairs. However, since O(n)/2 is still proportional to the array size, its space usage is effectively O(n). Lastly, other variables like number, complement, and the sorted tuple only require constant space, or O(1). When we consider all these components, the dominant factor is the space used by the dictionary and the set, leading to a total space complexity of O(n). To put things into perspective, let's compare this optimized approach with the brute force solution. A naive approach would involve generating every possible pair of elements in the array and checking if their sum equals the target. This would require O(n)² time complexity, as generating all pairs involves a nested loop over the array. Checking each pair is O(1), so the overall cost remains O(n squared). As for space complexity, the brute force approach doesn't require additional data structures, so its space complexity is O(1). Now, with the optimized approach, we reduce the time complexity to O(n) by using a dictionary to track complements. However, this comes at the cost of increased space usage, as the dictionary and set require O(n) space. The trade-off here is clear. While the optimized solution uses more space, it significantly improves efficiency by reducing the time complexity from O(n squared) to O(n). To solidify our understanding, let's look at a mathematical justification for the optimized approach. Both dictionary insertions and lookups have an average time complexity of O(1), thanks to hash-based access. Similarly, insertions into a set also take O(1) on average. The algorithm involves a single traversal of the array, which costs O(n), and there are no nested loops or additional iterations. This ensures that the dominant term in the time complexity remains O(n). On the space side, the dictionary grows linearly with the number of unique elements in the array, and the set storing unique pairs also scales linearly with the input size. Thus, the space complexity is O(n). In summary, the optimized approach is a significant improvement over the brute force method, reducing the time complexity from O(n squared) to O(n), while leveraging additional space of O(n) to achieve this efficiency. When solving problems involving pairs with a given sum, there are several common mistakes to be mindful of. First, forgetting edge cases can be a major issue. For example, arrays with negative numbers, zeros, or duplicate values might break your logic if they're not properly accounted for. Imagine the target sum is 0, it's easy to overlook that -1 and 1 together equal 0. This happens when we make assumptions about the input that don't hold true universally, leading to failed test cases. Another frequent mistake is relying on nested loops for large inputs. While a brute force approach that checks all possible pairs might work for small datasets, it quickly becomes inefficient as the input size grows. For instance, with n larger than 10,000, this O(n squared) approach becomes impractical. Instead, optimized solutions like hash maps can reduce the time complexity to O(n). Lastly, modifying the input array during processing is a pitfall to avoid. Removing elements while iterating can cause index errors or result in missing values, leading to incorrect output. To handle this, use auxiliary data structures rather than altering the original input. Incorrect handling of hash map keys is another frequent source of errors. For instance, failing to check whether the complement exists in the hash map before attempting to use it can lead to accessing undefined values or missing valid pairs entirely. Additionally, when using two-pointer techniques, not properly accounting for duplicates can cause problems. If duplicate values aren't handled carefully, you might end up with repeated pairs or miss some valid combinations altogether. Beyond avoiding mistakes, there are important strategies to keep in mind for interviews. Recognizing patterns in the problem is crucial. For example, determining whether sorting, hashing, or dynamic programming is the most appropriate tool for the task. Interviewers also value your ability to articulate trade-offs. If you choose a hash map for O(n) time complexity, explain why you prefer it over a two-pointer approach, which uses O(1) space. Practicing hash map logic is vital, as many problems require checking for complements efficiently while iterating. Finally, always be ready to discuss time and space complexities. For example, you should know that a hash map solution runs in O(n) time and uses O(n) space, while sorting-based methods may reduce space usage at the cost of a slower O(n log n) runtime. This problem is closely related to several other classic coding challenges that you should practice to deepen your understanding. One foundational example is the two-sum problem, where you find two numbers that add up to a target value. This logic can be extended in the three-sum problem to identify triplets that sum to 0, or even further in the four-sum problem, where quadruplets satisfy a given target. Another related challenge is subarray sum equals k, which shifts the focus to subarrays and often requires techniques like prefix sums and hash maps to solve efficiently. When it comes to alternative approaches to solving pair sum problems, brute force is the most straightforward. This involves traversing all possible pairs and checking if their sum matches the target. While simple to implement, it's inefficient, with O(n squared) time complexity, making it impractical for larger datasets. A more efficient approach leverages hash maps to store scene values. As you iterate through the array, you check if the complement of the current number exists in the map. This solution runs in O(n) time, but the trade-off is that you need additional space to store the hash map. Another efficient technique is the two-pointer approach, which works by first sorting the array. Then, you use 2 pointers, one starting at the beginning and the other at the end, to identify pairs that sum to the target. This method is space-efficient, requiring only O(1) extra space, but sorting the array adds an O(n) log n time complexity. Yet another alternative is binary search. Here, you sort the array and, for each element, use binary search to find the complement that matches the target. While this method also has a time complexity of O(n) log n, it's typically slower than hashing for larger datasets due to the repeated binary search operations. Each of these approaches has its own trade-offs, so it's important to choose the one that best fits the problem constraints and input size. Understanding these variations not only prepares you for interviews but also strengthens your problem-solving toolkit for a wide range of coding challenges. Great job! We've explored problem number 1951, all the pairs with a given sum, and reviewed both brute force and optimized approaches. Remember the key takeaways about using hash maps and analyzing trade-offs. Keep practicing, and don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!